Hello, everyone. Thank you for opening this video. In the next few minutes, I'm excited to guide you through our tool, FaultWeave. FaultWeave is a three-plane architecture for scalable chaos testing, a React control plane for experiment management, a Spring Boot orchestration plane for lifecycle coordination, and a Kubernetes data plane where Envoy sidecars use a record and replay mechanism for efficient simulations. To run FaultWeave, start with a working Kubernetes cluster and deploy your system under test on it. In our demo, we use the open-source benchmark train ticket, pull its official manifests, and in each microservice deployment, add the OpenTelemetry settings so that W3C baggage propagates end-to-end. Apply the manifests and bring the system up. Next, deploy the toolchain. FaultWeave is built on the Chaos Blade ecosystem. The core components are Chaos Blade Space Exploration, Chaos Blade Box, and Chaos Blade Fay. In space exploration, set environment variables, build with Maven, then run /build-and-deploy.sh to build images and deploy services. Verify with Docker/. Then go to Chaos Blade Box, package with Maven, build the Docker image, and start the service. This is the microservice gateway. Finally, in Chaos Blade Fay, run npm install and npm run dev to launch the UI. You're now ready for Phase 1 recording and acquisition, and Phase 2 baggage-guided end-to-end execution. FaultWeave provides a guided 5-step creation workflow aimed at simplifying and structuring the process of defining complex end-to-end resilience tests. The workflow begins with the selection of the system under test. After the user specifies the entry API, the platform will automatically render a topology map off the service call chain, thereby visualizing the complete dependency relationships, including critical paths and branches. The fault configuration stage supports the interactive selection of target services on the visual topology map and the application of predefined fault models, such as CPU, memory, network, or container issues. Subsequently, the user is required to define the quantitative success criteria for the experiment, namely service-level objective assertions, and configure the corresponding concurrent load and duration. Upon completion of this process, the system will generate a resilience exploration task containing complete context, precise targets, and clear SLOs, which supports subsequent one-click execution. The FaultWeave drill record page provides a comprehensive snapshot of a completed chaos experiment. The basic information bar at the top displays core metadata, such as the task ID, entry API, final status, and total runtime, offering a quick overview of the drill. The execution logs section records the batched test execution process. The system uses parallel batches to avoid overloading the cluster, and the log entries allow users to precisely trace each stage's execution for rapid troubleshooting. The test case information overview cards provide key metrics on the completion status of test cases and services, helping users quickly assess the drill's completeness and confirm if all scenarios were covered. The execution results table delves into each independent fault scenario, with each row displaying key performance indicators like P95/P99 tail latency and error rate, along with their SLO compliance status. The table clearly identifies the injected fault type and supports powerful filtering to help users focus on specific scenarios or high-risk faults. Cross-analyzing this data can reveal deeper resilience issues. For example, meeting latency SLOs while breaching the error rate SLO typically points to flaws in fault-tolerant strategies like retries and circuit breakers. Conversely, breaching latency SLOs with a normal error rate suggests performance bottlenecks or capacity issues. The AI-generated test summary at the bottom of the report provides a quantitative resilience score, highlights typical failed test cases with root cause analysis, and analyzes the fault propagation mechanism. Most importantly, it directly identifies the system's weak points and offers actionable improvement recommendations, such as adjusting timeouts and retries, configuring circuit breakers, or implementing auto-scaling.